Hi everybody, and welcome to another JASP tutorial video. Today I'm going to do a more in-depth tutorial than I've done in the previous ones, just because this particular analysis for this video is quite a bit more involved, we'll say, than the previous videos in the playlist here. We are going to be doing analysis of variance, or ANOVA, in this video. And the menu structure for ANOVA is going to get quite a bit more involved, and there's lots more options. And so the makers of JASP have included a menu structure, a collapsible menu structure. Before we get started, I want to go ahead and let you know that as of this video, the recording date of this video, the JASP team has introduced JASP Preview Release 0.10.1, added a couple of new features. I'll highlight some as I have noticed them. I'm not going to go through the whole release notes. You can catch that on their website, jaspstats.org. So let's jump into it. Okay, so I've opened the file that I've been working with in my previous videos, real data that I've had for several years now, and we're going to go ahead and do an ANOVA. And for this video, I'm just going to do a one-way ANOVA, and that is one independent variable and one dependent variable. And independent variables in JASP are called fixed factors. And one of the requirements for this fixed factor is that it has to be a categorical variable. And you can see here that it'll accept the two types, nominal and ordinal. Now, we're going to use the trace condition variable that I've mentioned in previous videos using this data. It has ordinal here. I just haven't changed it to the nominal character. It's essentially the same thing. So I'm going to go ahead and that's the independent variable. There are three groups, which is why I can't use a t-test. T-test, I have two groups, but only two groups. In the analysis of variance, in this analysis, we can use three or more groups. Now these are independent groups, so this ANOVA has to be with between subject levels of an independent variable. And that's what this condition is. This trace condition was a person didn't trace anything, they were in a fluent trace condition or a disfluent trace condition. And for the dependent variable, I'm going to go ahead and use one that we've discussed in other tutorial videos. I'm going to use the incongruent accuracy. So what was their score? And I'm going to put it over in the dependent variable box. As you can see, it's got a ruler because it's a scale variable, and that's what dependent variables are in analysis of variance. Just like t-tests, the dependent variable, the outcome variable, needs to be continuous. Okay. One of the new features in 0.10.1 is this button to arrange the sorting of your variable list over here. So we can click and we can get no sorting, and we can get sorting by name or sorting by type. Type refers to the type of variable image here on the side, so nominal, ordinal, or scale, and then by name it just takes the first letter and sorts it alphabetically. And as you can see, the image here is A to Z in any case. The default sorting is by variable order, as you can see from the grid here. Subject is first, average neutral accuracy is last, and that's what we end up with in the list here. You can change the sort if you'd like. Okay. Next, the WLS weights. These are the weighted least squares. Okay. So this is where you would specify if one of the variables in your groups has more weight, therefore, and then should be considered more informative. We are going to skip this because I don't have that a priori selection for this variable, so we don't need to worry about that. We're going to skip that. You can find more about WLS weights in the help menu for JASP. Okay, so moving on to the options for this test. Now you can see over here on the results window, in the results module, that it's already calculated a basic ANOVA for me. Basic ANOVA, and you can see here that in the ANOVA, just above the table, and this would be the source table, if you ever had to calculate ANOVA source tables yourself before, generally speaking, all of the information in the source table leads to your F and P values. Now, above the source table, you see the word ANOVA, and you see the DV. You can copy that. You can add a note to this particular table. But in general, the basic ANOVA that you get is your variable name, trace condition. This is your IV, so all conditions of your IV in this ANOVA, and then underneath it is your residual or your error. JASP makers decided to go with residual in this case, but if you ever made a source table, you'd likely put error here. Residual, generally speaking, comes from regression stuff, which, of course, in the general linear model, the ANOVA and regression both fit, so residual works here no matter what. And then for both of these, you get the sums of squares. This value is the total sums of squares for that particular line. This ANOVA table does not give you the total line. You might actually see IV, residual, total. The JASP makers decided that that part isn't useful. Then you have the degrees of freedoms values for, I don't know why I said freedoms, degrees of freedom values for the trace, for my trace condition, for my IV, and then however many residual degrees of freedom that I have, okay? Now, in order to get mean square, you divide the sum of squares by the degrees of freedom, and so that this value here, where my cursor is, divided by 2, gives me my mean square of this, okay? The sum of square values for the residual divided by the degree of freedom residual value leaves me with this mean square error value. This is the mean square error, because this is the error line. So mean squared treatment divided by mean square error, or mean square residual, leaves me with an F value. That's the F ratio. The numerator is your independent variables mean square, and the denominator is your error mean square, and that gives you F. F is a distribution that has a consistent distribution, so we, from F of 1.817 with degrees of freedom 2 and 60, we can determine a p-value from that. As you can see, the basic ANOVA on this table, this would not be a significant null hypothesis test, and therefore we would fail to reject the null hypothesis. Okay, so let's go through some of these options here. I'm not going to go into too much depth in all of them because this video would probably top 30 minutes, and I don't want these tutorial videos going too long as some of them have gone in the past. So let's go through some of them. So if you wanted to specify model terms, you would do so in here. So if you wanted to specify what independent variables are in the model, you can move them from components to model. By default, all of the independent variables, and this will become more apparent when we do a factorial, when I have more than one fixed factor, I can go ahead and rearrange model terms over here in the model terms box. Okay. So I'm going to save that for when we have interactions and things. The second thing you'll notice in the model options drop down is the sum of squares type. Okay, so by default, type 3 sum of squares, and you can see it's in the note, type 3 sum of squares is used. This is the most common type of sum of squares that are used in ANOVAs and in the vast majority of social science research. This is technically partial sums of squares. It reduces error, and it's usually used when you don't have issues with assumptions. You would use type 3, and by default, that's fine. Okay. Type 2 is when you have unbalanced data. Okay, so if there's too much variance in one level of your independent variable versus not enough variance in the other, so you would correct some of that imbalance with a type 2 sum of error, and this is a drop down. Type 1, on the other hand, is when the order of the model factors is important, which will then change the sum of squares values for later in this model sequence. So this one is the least often used in my area of research and in many social sciences. So again, you could probably just go ahead and leave that as type 3. Okay, so I'm going to go ahead and close that, and let's jump into assumption checks. So we've probably seen some of these before, but one of the things that is important for ANOVAs is that the variance of the two, or of the 3 or more levels of your factor have homogeneous variance. That is, the variance is relatively equal. So you can go ahead and click that, and it'll give you the equality of variance Levines test. And this is the similar Levines test to the independent samples t-test that we did in a previous video, in a previous tutorial. And again, you would choose a criterion value as to whether or not you do have equal variances. And so you look at your p-value based on that criterion, 0.05, 0.01, 0.001, on a sliding scale of conservatism, respectively, and you would use this information and this p-value to determine whether or not you have equality of variances. And it seems to be with an f of 1.2 and these two degrees of freedom values, which come from our degrees of freedom ANOVA table, that with a p of 0.31, we're probably fine with equality of variances. That is, my 3 groups, my 3 trace condition groups, are fairly equal in their variances. You can click homogeneity corrections, so either no correction, which turns on this value here, this column in your ANOVA table, as just in homogeneity correction. So for this one, I don't need it. It is offered as an option so you can compare it with the other 2 kinds of corrections, the Brown-Forsyth or the Welk. Okay, and you can see here that neither correction does much of anything to my trace condition variable. Sums of squares don't change. But what does happen is the residual sums of squares is modified by the degrees of freedom. Okay, so the sum of squares doesn't change, but the degrees of freedom does, which means the mean square error changes. So you would use these corrections if this test told you that you may have problems with unequal variances. Okay, and you can see my mean square changes, which then changes my F, which then changes my p-values. Now, of course, I don't have problems with equality of variances in this, and so F and P don't really change too much with significant degrees of freedom reduction, like the Weight test over here. Okay. You can also get the QQ plot of residuals. This plot tells you whether or not your residual values are normally distributed, and you can see here that it's about right. So we don't need to worry about our residuals and violating that assumption. Okay, so I'm going to go ahead and leave that on here as we move to contrasts. So contrasts are, generally speaking, planned comparisons. So you have an a priori idea about which levels are going to be different moving forward from the ANOVA. Because really, if this was a significant result, according to our p-value, p is less than 0.05, typical alpha, we would need to know where the difference is, because the omnibus test, this one, just tells us there is a difference. What we need to learn from contrasts or post-hoc tests, which we'll go over in just a minute, is where the difference is among the levels of my independent variable. And that's what we can do with contrasts. Now, I'm not going to go through all the different kinds of contrasts, but JASP offers deviation contrasts, simple contrasts, difference contrasts. Generally speaking, these are common when you're just trying to find if there is a difference, hence the name difference. Helmholtz, repeated contrasts, and then polynomial contrasts. For those of you who are familiar with SPSS and ANOVAs, polynomial contrasts are very common when you take a look at this. Very briefly, so these are the four, according to very quick definitions. You can find out more, again, in the help section of the JASP program. Deviations, the mean of each level of the IV is compared to the overall mean. That's pretty common. Simple, compare means to a specified level, so maybe a treatment to control. So we might do a simple contrast to just determine if means are different. But again, this has to be a priori. Simple difference. Okay, so this is a reverse Helmholtz. The mean of each level is compared to the mean of the previous level. Helmholtz is the opposite direction. Okay, the mean is compared to the subsequent. Okay, so previous mean, subsequent mean, repeated. The mean is compared to the mean of the following level. Okay, and then polynomial is doing a trend analysis. Let me get there. Polynomial is doing a trend analysis to see if it's not actually a line, but a curve of some sort. Okay, and you can check this box if in the assumption checks here you have equal variances. Of course, we can assume equal variances, and then we can get confidence intervals for those contrasts. So I'm going to go ahead and click simple for trace condition, and I'm going to click confidence intervals. You can see what that looks like. Go past my QQ plots here, and we have my levels in the comparison, the estimate for the mean difference, the standard error for that estimate, because again there is some uncertainty from due to sampling. Okay, degrees of freedom for this comparison, the t-value because it's a pair of levels, I can do an independent samples t-test, technically. That's what this t-value is. And then that t, again, has a degrees of freedom from its table. We can find the p-value, and then we have a 95% confidence interval for that mean difference, which is the estimate here. Okay? So that's just one kind of contrast. You can only do one kind of contrast at a time, because if I decided to select a deviation, it would go ahead and do the deviation and replace the simple contrast with the deviation contrast. And you can see 2 to 1, 2 to 2, 2 to 3 leaves us with this value, and then again we get the same sort of issues moving across the values that we get. Degrees of freedom, t, p, and our confidence interval. So I'm going to go ahead and leave that up. Let's jump into posthoc tests. So imagine here you didn't have a priori idea about where the difference would be, if this was a significant test, of course. And so you end up with a significant result. And so you're like, oh, crap. Well, I don't know exactly where the difference is, and so I want to go ahead and add some additional comparisons between my levels. And generally speaking, those comparisons are pairwise. However, if you do those comparisons, you ultimately inflate alpha from the original omnibus test, increasing your chances of making a type 1 error. Type 1 error is saying that there is an effect when there isn't one in real life. Okay? That's why we make our alphas really small, so we don't make that kind of error. And so posthoc tests include what are called corrections. And the top 3 are the most common corrections that you'll see out there, but then there are 2 additional ones that JASP creators included, the Holm and the SIDAC. If you are coming from SPSS, not all of them are included in here. So, SPSS has quite a bit more post-hoc corrections, but we can go ahead and just jump into here and take a look at what the results look like, the results output looks like if you do a post-hoc test. So by default, the Tukey test is selected. And so if you move your independent variable into the posthoc window here, it will automatically produce a Tukey. But you can go ahead and select additional ones. You can get confidence intervals for your mean difference that is created in your pairwise comparisons. You can have it bootstrap, which is going to take some CPU time to complete. Okay, as you can see by these rotating circles, that's it working. Okay, bootstrapping is just additional simulations for the correction. Okay, as you can see here, it's done. And the bootstrapping will give you further information about your mean difference value, so whether or not there's deviation in the 1,000 times that we simulated this mean difference. Is there any bias? And we can see here that these biases are very small, and so there isn't much going on with resampling over and over and over again. Okay, so we can do that each time. We can also select our additional corrections. We can do a Chaffee test. A common one that I use in my research is the Bonferroni correction. And what you see in the posthoc test table here is that you get a p-value for these tests. That's the adjustment. That's where you see the adjustment. And so you use this p-value as your new p-value for that represents this t. And so this is compared against a corrected 0.05. Okay, that's what the correction is happening under the, so you can just compare it to 0.05. It's not the same 0.05 as this p is compared to its corrected 0.05, okay, because this value is changed beyond just running a simple t-test. And if you were to do this and then do a t-test between levels 1 and 2, or levels 1 and 3, or levels 2 and 3, the 3 different tests, you will see that these values for p are different. And because the omnibus test is not significant here, the 0.171 that we got in the initial test, none of my posthoc tests are significant. There's no difference between any of these means, any of these 3 tracing conditions. We were very disappointed when that occurred, and so you can see here the repeat of my mine and my colleagues' disappointment in this data when we ran these tests. There are different types of corrections. Okay, standards, games, howl, done it, and done. You can go ahead and click on Holm and Sidak, by the way. Shidak. I don't know if I'm saying that right. And again, it just puts up additional p-value corrected p-values. So we can look at different types. I'm going to go ahead and save that for the help menu so we can move on to descriptive plots. Descriptive plots, generally speaking, with one factor, you'll put that on the horizontal axis and it will generate a line graph for you. You can display error bars. By default, it will display confidence intervals as the t-tests plots do, but for ANOVA, we can change that to standard errors. Okay, so the error bars are standard errors. And you can see here that the average incongruent accuracy for this is lowest in the disfluent trace condition, but the error bars overlap, which means that there really isn't a difference between the 3 conditions. Okay, that's descriptive plots. We'll talk more about descriptive plots when we have more than one factor. Okay, one of the great things about ANOVAs is plotting and the wealth of information that you can get from an ANOVA analysis. And one of those additional options, here I am in additional options, is getting the marginal means for my conditions. So I have my trace conditions here, and I have my marginal means. This is actually, these means here are actually what are plotted. And there you get your standard errors, and so you don't actually have to do a whole lot to make a graph from this information. I actually created a YouTube tutorial about how to create a simple graph, bar graph, line graph, what have you, utilizing these 2 bits of information. I'll go ahead and plug it in the top right corner. Additional options you can get marginal means from bootstrapping. Okay, you can compare your marginal means to a 0. Okay, and then whether or not you want to adjust it by anything. Where I'm going to go ahead and not uncheck those because bootstrapping slows us down here. We can get more descriptive statistics that'll just give us our standard deviation. You can see the marginal means are exactly the same as the means. The marginal means will become more important when we have more than one factor and we're doing factorials. Estimates of effect size. This is really important. Okay, this gets added over here at the top in the omnibus test. We have 3 effect size measures that we can add on here. Eta squared, that is the lowercase Greek symbol eta, ETA. So eta squared is when you get the estimate of the effect size for the variable in general. Okay, with one variable like I have here, eta squared is fine. A recent study suggests that it overestimates the population variance, so comparing across studies isn't all that useful. So 1 eta squared in one study does not equal the same as another study, and it's probably not a good idea to compare both. Partial eta squared is perhaps the best one, and this is most useful, and you see you get the eta squared with a subscript p, okay? It solves the problem of overestimation, and it's most similar to Cohen's d value, okay? When you have multiple factors, you actually want to use partial eta squared, because this value is the variance for that variable, and that variable only, or interaction term, that a variance explained. So here you can see eta squared and partial eta squared aren't different, because we only have one variable, trace condition. And so they're the same. This one variable accounts for 0.057 of the variance, or 5.7% of the variance in incongruent problem accuracy. Okay, but if I add another factor, which we'll discuss in another tutorial video, if I add another factor, then partial eta squared values for those individual factors and interaction terms will be different from eta squared. Omega squared is, generally speaking, for repeated measures or when the sample size is small. Okay. Okay. You can also get the Vovk-Selke maximum p ratio. As in my other videos, I'm going to go ahead and skip that one. Closing options here. Simple main effects. Okay. Simple main effects are used, so we're not going to be using them in this one, when there's an interaction term present. So we will skip this for now for this one-way ANOVA tutorial, but stay tuned for the factorial ANOVA tutorial where we discuss simple main effects. Non-parametrics, this is what happens when I run into the situation where I've violated an assumption of normality, what have you, for the parametric ANOVA, and so the non-parametric ANOVA is called the Kruskal-Wallis test, if I'm pronouncing this one correct. So I'm going to go ahead and put it over in the trace condition and over into the box, and we will find our Kruskal-Wallis test. There it is. It doesn't have its own main titling, so it could get lost. Gives us a test statistic. It has a degrees of freedom associated with it and a p-value associated with it. And as you can see, the result would be the same. It would just depend on what I need to report. Speaking of reporting, as I have now finished here, I'm going to go ahead and throw up in this area over here, the standard APA notation for this ANOVA. Rather simple. I'll just throw it up in a little text box. But that's going to do it for this tutorial video. Please leave your feedback and comments down below. Thank you for watching. Bye-bye.